Hi everyone, this is Prof. K speaking, and today we're going to talk about phase diagrams. Our learning objectives for today is to explain the construction and use of a typical phase diagram. And then we're going to use phase diagrams to identify stable phases at given temperatures and pressures, and to describe phase transitions resulting from changes in temperature or pressure. And then we're also going to describe what a supercritical fluid phase is and potentially how it's used. So phase diagrams. So last time I drew sort of the triangle where we have gas going to liquid and liquid going to gas. And what a phase diagram does is it combines a plot of pressure versus temperature with identification of the phase that exists at different pressures and temperatures so that we can describe where a particular transition will happen and at what pressure and temperature certain phases exist. So if we look at this phase diagram, if you want to go from a solid to gas, you'll undergo sublimation or you'll cross this line at the bottom. If you want to go from a gas to a solid, you'll cross the line going you'll cross the same line, but in the other direction. If you want to go from a solid to a liquid, you have to melt your compound. If you want to go from a liquid to a solid, you have to freeze your compound. If you want to vaporize your compound, which is a liquid, got to cross the vaporization line. If you want to go from a gas to a liquid, you want to cross the condensation line. And you'll notice that on this plot, in addition to what I described in the last video, there's also two new points, which are described as the triple point and the critical point on this phase diagram. And so what does that mean? The triple point is the temperature and pressure pair, or the combination of temperature and pressure, where you'll have solid, liquid, and gas in equilibrium. So on this plot at 0.6 kilopascals and 0.01 degrees Celsius, you will have ice, water, and gas all existing together at this point. And so the dynamic equilibrium here isn't just that of between two phases, but three phases. And these other lines here, so this line represents the temperatures and pressures where ice and water are in a dynamic equilibrium. So ice plus liquid in equilibrium. This line down here is solid and gas in equilibrium. And then this line here is liquid and gas in equilibrium. And the critical point is the temperature and pressure pair above which supercritical fluid exists, which still doesn't explain what a supercritical fluid is, but it basically says when you get above this pressure and temperature over here on this portion of the plot, you're going to have a phase called supercritical fluid. So what is supercritical fluid? So supercritical fluid is a phase where your physical properties of that material, in whatever phase it looks like, is some intermediate between the liquid and the vapor phases. And so what this ends up meaning is that you have a much higher density than you would have in its gas phase. And so liquids typically have higher densities than gas, and the supercritical fluid also has a higher density than gas, but probably not as high of a density as the liquid. It expands to fill containers like gas. So if you had a box, or a cube, I guess, that you wanted to fill, if you filled it with a liquid, you'd expect it to only fill half the box. But if you fill it with supercritical fluid, it fills the whole box up like a gas, even though it has a higher density. These supercritical fluids also exhibit low surface tensions and viscosities. So if it has a low surface tension, what that means is that it potentially has weaker intermolecular forces than a liquid, but potentially slightly higher intermolecular forces than a gas because it is more dense. And a viscosity, like we've talked about, is its ability to flow. And so what this means is that this flows well. And so part of the way that it fills this room is by being able to spread out well. So it's good, and it sort of can take the space that it has while still having a higher density. And so one of the reasons why we like talking about supercritical fluids is they're really good at solvents because they can penetrate small openings. They travel around like a gas, and then you can change the temperature and the pressure, turn it into a gas, and potentially cause some portion of it to leave or some portion of it to dissolve something. And so it's really useful. Supercritical CO2 is used really often in the food industry. You could use it to decaffeinate coffee and also in lots of other food sciences, some of which your book talks about. And so it's useful to know about because it's a different physical state that we can exist in that maybe you haven't encountered before unless you've seen it in a chemistry course. And so how do we actually use these phase diagrams and use the information that we have? So one of the questions we might face when we're looking at this plot is, at what phase of water would be present at 101 kilopascals and 90 degrees C? So 101 kilopascals on this plot here is this line. And then 90 degrees, we might guess, is here on this plot. So the intersection of this temperature and pressure pair tells me that at this phase, I'm going to have liquid water. So I can use information in this phase diagram to help me guess what phase I'll have at certain operating conditions for my system. Another thing that it lets us do is see how our phases can change if we change temperatures or pressure. So if I start at 0.6 kilopascals and 0.01 degrees C, or I start at the triple point here, and I increase the pressure of my system, how does the phase change? So if my temperature stays the same, but I increase the pressure, what happens? So if you're at the triple point, then we start with a mix of gas, liquid, and solid in equilibrium with each other. And then if you increase the pressure, we move into the liquid phase. So you can describe how the mix of your components will change based on what you're doing to your system using a phase diagram. You can also see that if instead of having this sort of depiction of ice as sort of tilting backwards, if instead our ice and solid phase look like this, then if I increased the pressure of our system from the triple point, we would have formed a solid. So the slopes of the lines, or the ways that ice and water are exchanging with each other, help us predict what phases we're going to be. And so people created these curves by doing a lot of tests where they took water in a system and they started at some low temperature and pressure, and they said, if you come here and we have this low temperature and pressure, we get ice. If I increase the temperature, it stays ice. And you keep doing that. And what they found is that if you go to 0 degrees and then you increase the pressure past 100 degrees, they found water. And so they mapped this out. So they create these plots where they see how you can vary temperature and pressure so that we can make predictions based on this. And so that we can do some interesting chemistry based on the phases we are or the phases we want to move between. And so this is another tool that we use as we continue to talk about phase transitions and the ways that we can navigate the changes from one phase to another.